Well, I hope everybody enjoyed that first exam as much as I did. The first thing I'd like to cover out of Chapter 4 is Section 4.2, which is the mean value theorem and Rolle's theorem. These are both theorems dealing with average and instantaneous rate of change and how they occur together for our differentiable functions. So first we have Rolle's theorem. If f of x is differentiable on the closed interval a to b, or technically on the open interval as long as it's continuous on the closed interval, not a whole lot of difference there, and the endpoints evaluate to the same value, that is f of a equals f of b, then there exists an x value c in between a and b where f prime of c is equal to 0. So what this says in a picture, if I have an interval where my function values is the same at the endpoints, then somewhere in between I'm going to have a slope of 0. And the reason this works in sort of a pseudo-proof with pictures is, first, if a and b both have the same sign derivative, that is, they're both going up there, they both have positive derivative, or they both have a negative derivative, then I can do this little cheesy thing with the intermediate value theorem, saying I have a spot a little bit above, and I have a spot a little bit below, and somewhere I have to connect the two, giving me a third point where the function values are equal to the endpoints. With that out of the way, I basically go ahead and assume that the sign on the derivative for a and b are different. So it's either going up and then down, or going down and then up. And in either case, I get to use the intermediate value theorem again, but this time I get to use it on the derivative. Because here I have f prime of a is greater than 0 and f prime of b is less than 0. And since my function is differentiable, that means my derivative will also be a continuous function. And so here the IVT says, the intermediate value theorem, says that in between a and b there must be a c where f prime of c is equal to 0, because it's positive on one side and negative on the other. And the same thing happens over here. I have f prime of a less than 0 and f prime of b greater than 0, and so IVT says the same thing. The mean value theorem is very similar to Rolle's, but it's a lot more generalized. If f of x is a differentiable function, again on the closed interval from a to b, then there exists an x value c between a and b where f prime of c is equal to f of b minus f of a all over b minus a. Or in other words, this is saying that the instantaneous rate of change, there's a spot c where the instantaneous rate of change is equal to the average rate of change. So you can see that this is a lot like Rolle's theorem. It's just now I'm missing the condition that f of b is equal to f of a, and so I have a correspondingly different result. So by the same token, I can consider Rolle's theorem to be the special case of the mean value theorem where f of b is equal to f of a. So I could just go along and assume that I'm doing mean value theorem every single time and just use the endpoints equal to each other when I need them. So I could say the MVT is equal to Rolle's minus f of b equal to f of a. They both achieve similar results. Proving the mean value theorem is a little bit more involving than it is for Rolle's theorem, but it's actually still pretty interesting. The ultimate goal for the mean value theorem is that if I have a nice function and I pick an interval from a to b, then when I find the average rate of change on this interval, I can find a corresponding point where the instantaneous rate of change, or the slope of the tangent line, is equal to the average rate of change, or the tangent line is parallel to the secant line. But this can be really hard to do in general, so I'm going to do some things to rig the result, so to speak. As first, I'm going to make a line. Specifically, I'm going to make the line between the point A, comma, f of A and B, comma, f of B. In my picture here, this is the secant line. It's going to be the dotted line I have on the picture. So I have 2 points, so I can find the slope, and I can pick one of the 2 points to make my line with the point-slope form of equation of the line. So I'll have y minus, I'm going to pick the first point, y minus f of A would be equal to the slope between the 2 points, but the slope between 2 points is just going to be f of B minus f of A all over B minus A. Rise over run. And this is multiplied by x minus A. Or I can write y equals f of B minus f of A all over B minus A times x minus A plus f of A. So I'm going to call this L of x. It's going to be my line. And what I want to do with this line is I'm going to make a third function, h of x. We'll call h of x equal to f of x minus L of x. And what this has the effect of doing is it takes my previously possibly slanted function and it subtracts a line and kind of makes it flatter a little bit. But we notice something interesting happens. F of x is already differentiable. L of x is a line, so it's definitely differentiable. And so the difference of 2 differentiable functions is again differentiable. So I can say h of x is differentiable. And something great happens. H of A is equal to, of course, f of A minus L of A. But my line, as I've written it above, is this nasty looking piece of work. F of B minus f of A all over B minus A, more parentheses, when I plug A in for x for my line, I end up with A minus A over here, which becomes 0, which is multiplied to the biggest, nastiest part of this. So this is equal to f of A minus 0 plus f of A, which is going to be equal to f of A minus f of A, so this is equal to 0. And similarly, h of B, which would be f of B minus L of B, would be equal to f of B minus this big old thing and now what happens? The B minus A's cancel, leaving me with f of B minus f of A plus f of A in the inside. So now the f of A's cancel, leaving me with f of B minus f of B here, so the f of B's cancel, ending up with 0 again. So now h of x is a differentiable function, and on the endpoints of the interval from a to b, it's equal to 0 for both points, which means I can apply Rolle's theorem to my h of x. So by Rolle's theorem on h of x, there is an x value c in a to b where h prime of c is equal to 0, because h of x was a differentiable function, h of a was equal to 0, and h of b was equal to 0. But h prime of c is equal to f prime of c minus L prime of c. But L prime of c, the slope of this line, is going to be exactly, f of b minus f of a all over b minus a. But since h prime of c is equal to 0, I have, in the end, that f prime of c is equal to f of b minus f of a all over b minus a, which is exactly what we were supposed to get according to the theorem. And this is all fine and dandy and everything, but how do we use them? Well, for one simple problem, I can ask something like, if f of 1 is equal to 3, and I know that f prime of x is greater than or equal to 2 for any positive x value, I can ask, what is the smallest possible value of f of 5, for example. So if I'm in a situation where I know the value at the start, and I know a minimum rate of change, or minimum speed, for example, I can estimate the minimum distance traveled, question mark. Then I'll be looking for something between f of 1 and f of 5, and this should say that between f of 1 and f of 5, I can calculate the average rate of change. So f of 5 minus f of 1 divided by 5 minus 1 is equal to f prime of c for some c in 1 comma 5. And this is by the mean value theorem. But according to the question, the derivative is always greater than or equal to 2, which means f prime of c here must also be greater than or equal to 2. So that says 2 is less than or equal to f of 5 minus f of 1 all over 5 minus 1, which is equal to 4. Which means I have 8 is less than or equal to f of 5 minus f of 1. But I know that f of 1 is equal to 3. So I can replace that. I can say 8 is less than or equal to f of 5 minus 3. And I can solve for f of 5. I know that f of 5, let's add this first. 8 plus 3 is 11. 11 is less than or equal to f of 5, which means f of 5 is greater than or equal to 11, or f of 5 must be at least 11. Which says that 11 is the minimum possible value for f of 5. Perhaps a more useful variant of this problem is if I know the current position, or if I know a position at a certain time, and I know a maximum possible speed for an object, then I can calculate the maximum possible distance traveled by the object. So if I, for example, lose a golf ball, I can theoretically use calculus to reduce the amount of ground I need to cover while looking for the golf ball. A more abstract example of something we could have is similar to what we did with the intermediate value theorem. Before we use the intermediate value theorem to say, oh, I can show that there exists a root to this equation somewhere in this interval by saying, oh, hey, it's negative on one side and positive on the other, so the IVT says there's a solution in between. But I can take it one step further now. I can prove things that have a maximum number of solutions. Or in particular, I can prove that something has exactly one solution. So I want to prove that 2x equal to cosine of x has exactly one solution. And the way I do this is I start off by showing there's at least one solution. And that's with the IVT. So how do I do that? I set up h of x equal to cosine of x minus 2x. and I want to find out where h of x is equal to 0, or if h of x is equal to 0 ever. So I'll try a couple of points. Let's try h of 0. This is equal to 1 minus 0. Okay, that's 1. That's positive. If I try, what's easy to calculate? Pi over 2, maybe? At pi over 2, cosine will be 0. Doesn't get much easier than that. Cosine of pi over 2 is 0, minus 2 times pi over 2. That's equal to negative pi. That is definitely less than 0. So according to the IVT, h of x has at least one solution in 0 to pi over 2. So we have the existence of a solution, and let's try to show that there is not more than one solution. I want to say show that there cannot be more than one. And this might seem kind of hard to do, but I'm going to cheat and suppose that there are two. If there's more than one solution, then I can find two solutions. I mean, if there's like 17 solutions, I'm still going to be able to pick two of them. So I'll suppose there are two or more. Well, since there exist two solutions for this function, and this function is differentiable, I should be able to use Rolle's theorem to try to find a spot where the derivative is equal to 0. So we'll say these solutions are x1 and x2. Those are my solutions. And we'll just go one further and say x1 is not the same as x2. Then by Rolle's theorem, there exists an x value c in between x1 and x2. So instead of not equal, we'll just assume that x1 is the one on the left and x2 is the one on the right. That makes this part easier to believe. There exists a c in between x1 and x2 where h prime of c is equal to 0. Great. But there's a big but here. H prime of x, the derivative of my function, is going to be negative sine of x minus 2. Right? H of x is equal to cosine of x minus 2x, so its derivative, the derivative of cosine, is negative sine. Perfect. Which means h prime of c, which is equal to negative sine of c minus 2, is equal to 0. But that means that sine of c is equal to negative 2. Now, where is the sine equal to negative 2? Nowhere. Because sine is always between negative 1 and 1, no matter where you are on the real line. So this is what we call a contradiction. I made an assumption and I got something which was totally silly, which means I must have been wrong about having two solutions, which means there is at most one solution. But what we found in part 1 was that there was at least one solution in that spot, and the second part says that there is at most one solution, or no more than one solution. So if I have at least and at most, then I must have exactly one solution. Unfortunately, none of any of this tells me where the solution actually is. The IVT gives me an interval of where I could find it, but it doesn't tell me exactly what it is. And finally, for a more tangible example, we'll consider this. So what we have is two stationary patrol cars are equipped with radar guns, are sitting 5 miles apart on a freeway. And as a truck passes the first car, the speed is measured to be 55 miles per hour. About 3 minutes later, the truck passes the other patrol car, and its speed is again measured to be 55 miles per hour. And we want to prove that the truck must have exceeded the speed limit of 60 miles per hour at some time. So first up, let's lay down some ground rules. At least here in America, we still don't have the technology for teleporting trucks, and we do not possess the infinite energy for instantaneous acceleration, which means the position of this truck is going to be a continuous, twice differentiable function, which means we're going to be able to apply Rolle's theorem or the mean value theorem if we need to. So let's say that we have a time variable t. We'll say t equals 0 when it passes the first car, and t is equal to 3 at the second. Then the question we're really asking about is, what is his average speed? Because the average speed is the only tool we have to reveal information about the instantaneous speed, and that's from the mean value theorem. The mean value theorem, given an average rate of change, I know there exists a spot in the middle with the same instantaneous rate of change. So his average speed would be his final position. Oh dear, I have made a mistake. I said t was in hours, but 3 is in minutes. So what is 3 minutes in hours? This should be 3 divided by 60. Because 3 minutes out of an hour is 3/60ths of an hour. So his average speed should read s of 3 over 60 minus s of 0 all over 3 over 60 minus 0. But his position after that time is just simply 5 miles further down the road. So I have 5 minus 0 divided by 3 over 60, which simplifies to 1 over 20, which is equal to 5 times 20 over 1. And this, of course, is 100. And this is in miles per hour. So his average speed between the two cop cars is 100 miles per hour, which means sometime during that trip, this truck was traveling at least 100 miles per hour, possibly faster. But that is the only speed that we can guarantee for this trip. So he gets a ticket. So next time we're going to do 2 sections, which is 4.1 and 4.3, and we're going to talk all about how the shape of the graph of a function can depend on the derivative, or second derivative of the function.